Thank you, everyone, for joining us today for this webinar entitled Achieve Successful Outcomes with AI in Process Optimization. My name is Charlie Schick, and I'm VP of Marketing here at Quartic, and I'll be hosting today's webinar. Joining me today as speakers is Control Automation Hall of Famer Russ Reinhardt and members of Quartic's Process Optimization team, Xiaozhu Wang, who's our Chief Data Scientist, and Manuel Tejada, who's our Customer Success Engineer. And they will tell you about the importance and successful use of AI in process optimization. The flow of our talk today is we'll start with Russ framing the journey of optimization in process industries and talking about the needs of AI in optimization. And this will set up Xiao to give you an overview of AI and how it can be applied to optimization. And finally, Manuel will give us a demo of ways our customers are using a process optimizer. So with that, go on to Russ. So I will.
Thank you, Charlie. And you need to release.
Yep.
So there we go. And now I can share my screen and start the presentation. Okay, I greatly appreciate the opportunity to be with everyone and do this presentation. Best wishes to everyone on it. Process optimization applications. There are many, the main title says. And I'm not going to go through all of them. If you want to scan over them, you can read them faster than I can talk them. But there are many applications for process optimization. All of these have the human playing a strong role in defining the objective function, defining convergence criteria, and it is not closed loop. And what we'd like to do is to move toward autonomy, which would mean closed loop. I'd also like to illustrate that there are many model types used in optimization. Steady state models, transient models, just a whole list of types of models. And one of the problems is that people have to understand one kind of model for one application, another kind of model for another application. All of these are unique approaches and they require a lot of learning. And it would be really nice to have one model that is used in all of the applications. And artificial intelligence, machine learning can move us in that direction. There are many issues that optimization needs to address. And again, I'm not going to talk about all of these, but I want to point out that there are many opportunities for optimization and many issues that need to be addressed. I do want to point out that automatic control is not optimization. And this does get confusing for some people that aren't familiar with either. Control keeps the process at set points. It doesn't seek to continuously improve. There may be optimization within the controller, especially horizon predictive control, but the optimization isn't balancing the costs to get to the set point with respect to the cost of the deviation. It doesn't provide an economic weighting when you have constraint violations. So while we do have optimization, it just tries to optimize the path defined to a set point, but not the cost to get there. On the other hand, part of control, we have real-time supervisory set point optimization. This usually uses steady state models and steady state economics subject to constraints to find the set points. But these are steady state models and they don't balance the cost of the transient or the time to get back there. It just says, get to this point, but I don't know how you're going to do it. So it would be very nice to integrate both control and optimization in here. There are, for autonomy to do optimization, there are several stages that would be required. One would be pre-processing of data to validate or to correct the data to make sure that we have the correct valid data. And typical techniques are listed there in the subheading. Once we have the validated data, then we can adapt a model to the changing process. And chemical processes are always changing, whether they're chemical or refining or food or materials or pharmaceutical, they're always changing in time, and we need to adapt the models to them. Once we have the adapted model, then we can do post-processing to remove outliers. If the process is changing, old data is no longer valid, and it should not be influencing the model. So once the model is, the data has all been satisfied, and we have the models, then we can use the model for optimization. But all of these stages are important, and usually there's a lot of humans' effort involved in all of these. If we're going to go to full autonomy, we need to have ways to do all that. One of the major barriers, in my experience, to autonomy in the process industry is the fact that managers are in responsible charge. They are criminally, personally accounted for some events, violations, spills, violations of environmental or injury to people. If it's something that the manager permitted, overlooked, then they're criminally accountable for it. So managers are risk adverse. They don't place their career and life in the care of new employees. They are involved in all the decision making. And I think they're going to be less trusting of the understanding that AI could have of all of the comprehensive views, even than a new human. Some of the issues are safety, compliance to contracts, regulations, and coping with unexpected outcomes on there. So what I'd like to do is to summarize what I think are the needs and opportunities for process autonomy. And the big one, I think, is going to be to establish credibility with management. And this can be done through lots of simulations, through implementations on non-critical aspects, on not having the optimizer, the artificial intelligence, be in charge, but have it reporting what it would recommend done to establish credibility with management. It certainly would be nice to use the same model in all applications. We use models for design training, and it would be nice to have one model. Our processes are always subject to internal variation and input variation, raw materials. And when we try to optimize, we don't want to optimize for the average outcome rather. We'd want to perhaps minimize the probability of undesirable extremes. So having the optimization understand what's really important to manufacturing is important. I mentioned control. We'd like to optimize an economic path rather than just the set points. I think it's very important to have the artificial intelligence explain its recommendations to the human in charge. And one of the problems with model predictive control is that the operators and engineers watching the controllers don't really understand why it's doing what it's doing. And so a lot of efforts recently have been to reveal to the operator the why, what the forecast results are going to be if the controller takes action now. And this helps establish credibility with the people that are in charge of the process. Humans need continually to add or adjust considerations as the humans understand the processes better. And so we need to make it easy for the human to adjust the artificial intelligence from an initial myopic view of what the situation is all about to a more synoptic view of all of the new issues that are being included. Artificial intelligence needs to cope with stochastic data. Processes are not deterministic. They're noisy, subject to disturbances, and we might have a phantom best misdirect the optimization. So maybe minimizing the worst instead of maximizing the best. And the last point on this slide is that we would like to maximize annual production metrics, not maybe a batch yield. So for instance, if we have 100 batches per year and the yield is 75%, this is actually better than if we can increase the yield to 80%, but in doing so slows production so that we're only getting 80 batches per year. The product here is 75. The product here is 64. So we would like to look at the annual production, not the batch lead. This is going to be available to all of the people that are looking at it. So I'm just going to say that I've got two more views that reveal the comprehensive view. And I'm not going to take the time to do it, but I'll just say that they're available for anybody who would like to see the presentations afterwards. And again, Charlie, thank you very much for inviting me.
Thank you, Russ. Thank you for that. And now on to Xiao.
Okay, great. Thank you, Russ, for the wonderful presentation on where we are and where we should go with process optimization. I'm just gonna quickly restate some of the points that Russ has discussed. Specifically, I just want to emphasize the two modern challenges of process optimization. So the first one is really scalability. As we all know, a good system model is usually needed to come up with a good control design for any process. And sometimes it's just not very feasible to design a good system model for a very complex, say, multi-unit process. Now, even if we actually did manage to do that, there's another question that if we can easily deploy that complex nonlinear optimizer and make sure that it always converges within a reasonable amount of online computing time. And secondly, process optimization for the most of the time is actually just about control, like Russ said, not optimization. That is, it separates control and optimization, and you need another layer to optimize for any given economic objective. For example, how do we actually come up with the best set points for all the control parameters for MPC that maximize yield, for example? And we believe that we can solve these problems with the AI already nowadays, with the correct setup and approach, of course. Just want to mention that when we say AI here, we really mean machine learning. And you know, the most common subfield of machine learning is probably predictive modeling. But can predictive modeling be the solution here? We all know that nowadays, for a lot of use cases, we can actually have a great model that can predict the outcome very well. But knowing how to predict doesn't mean knowing how to change it. What we really want is causality here, but we are getting correlation here. You know, but how you actually discover causality is an open research problem, and practically it might make more sense to just directly optimize the process instead of making a two-layer problem. And we are really dealing with you know, optimization with constraints here. Unlike, you know, high-tech companies like Google or Amazon, who are dealing with a big data, small stake problem, we are dealing with small data and a big stake problems. Just to give you an example, recommending a not so good book to one of the billion users you might have probably isn't such a big deal compared to, say, losing the entire batch or product for an industrial process. And small data, big stake really limits our ability to train best models offline, as well as you can't deploy models and iterate very quickly online. And to make things even worse, we can't experiment with a lot of degrees of freedom either, like due to safety or regulatory reasons. So our research team actually conducted quite a lot of experiments, and some of them actually got deployed for clients with great results, which Manuel will talk about in a while. But what we found is the variance of these three techniques, namely Bayesian optimization, offline reinforcement learning, and imitation learning, could potentially improve your process significantly. Now let's look at some examples. So the first one is a batch process on penicillin fermentation. It's a single unit operation, but it is challenging just because in total, you're actually tweaking about 70 to 80 cell points in total. And with just 10 offline batches, you can achieve 7% to 17% yield improvement, specifically with just the set points and the measured objective. We are able to get 7% improvement, and with additional real-time measurements like pH and temperature, the improvement can be increased to around 17%. And now, if you look at the recommended recipes, the AI algorithms sometimes agree with each other, sometimes don't. For example, the sugar feed rate on the left, looks sort of similar for all three AI algorithms, except for maybe some is more dynamic, others are a little bit stabler. For the pressure, though, they seem to disagree a little bit more if you look at the right side of the graph. And here we are not incorporating any operator expertise here. And as we said earlier, it's a small data, big state problem. But the AI algorithm actually really need sufficient data to thrive. So to complement that, it is really important to also try to incorporate some subject matter expertise if possible. And Manuel will show that a much more significant improvement can be achieved when you are combining, AI with the SME. So the second example we are looking at is a more continuous multi-unit process for atropine manufacturing. Here we are saying that we have a baseline controller, which is MPC controller, that is already running on production that help us collect data. And the question we're asking here is, can we enhance the performance with AI? And as we can clearly see on the left side, the AI algorithm managed to find a much better steady state than the original MPC data. Okay, I think that's all from my end. If you would like to learn more, you can visit our blog at quartic.blog. And thank you, and Manuel, you can take over.
Yeah, I'd like to do a poll question first. Let me put the poll question up and start the poll. So the first question is, are you currently applying ML to optimize your manufacturing processes? And will you do so, or will you do so in the next year? So just select a bunch of them there. There's different versions of yes, different versions of no, and some not sures. I'll give it a moment. Answer away, folks. All right. So we'll end the poll here, and it looks like if I look at the results here, I see that get a lot of yeses I'd like to, but don't know how, and some no currently. Those are the two top ones. So this is good, and you'll get more info as we go along. Thank you, folks. So Manuel, all yours.
Perfect. Thanks, Charlie, and thanks, Xiao. Now I'd like to put everything that Russ and Xiao have talked about into action by walking through how we've done this with our industrial customers. I'm going to start with an overview of the optimization workflow, so the minimum requirements that you need to get started and the levels of automation that can be achieved. My goal here is going to be to convey to you that the barriers to entry are not high, and it's actually likely that you're ready to implement some form of process optimization. Then I'll switch from the slide deck to our platform to demonstrate 2 optimization solutions that have been deployed for customers. You'll see that the impacts to the business are significant in both cases, although their complexity and level of connectivity with OT data sources vary greatly. My objective will remain the same, to show you that you're likely ready to implement an optimization solution. So as mentioned, I want to start by walking you through the workflow that we follow to execute one of these optimizations. We need to go from your idea of a use case on the left to an optimized process on the right. And to get there, we're going to use an optimization workflow. We'll start with the series of discussions with the process experts. And through these, we intend to understand the process and available data, as well as define the objective and constraints. Next, we will work with our data science team to formulate all of that into an optimization problem and deploy a user interface for process experts to get set point recommendations. The process experts will interact with that application to obtain set point recommendations, and those will be implemented on the process, and the workflow will repeat with the results used to update the underlying model. Now, 2 aspects that I've glossed over here that require further detail. What's the minimum data requirement when building these models? And how do we make the necessary data exchanges between your process controllers and this model? So that's exactly what I'm going to cover on the next 2 slides. Let's start with the minimum data requirements. So these are going to be the process set points and objective measurements, as Xiao mentioned. Not only are these readily available, but they'll allow us to do something very powerful. Understand how the parameters you can control impact the output you want to optimize. The underlying algorithm will make set point recommendations that are most likely to achieve the desired objective. Again, as Xiao mentioned, we can add more information to make this model even more powerful. We can build constraints on other secondary outputs and to further narrow the set points that are recommended to the user. And you've probably got uncontrollable variables like ambient conditions that influence your process. Those can be incorporated into the algorithm to modify the set point recommendations from day to day to always ensure the best possible outcome. In terms of data requirements, that's it. Now let's look at the levels of automation. By this, I mean, how do we pass process data to the application, and how are set points implemented on the process? So you'll see that we can make this very simple with a little bit of manual effort and no changes to your current operations, or we can implement optimal closed loop control. So on the left-hand side, you've got level 1, where we're doing offline set point recommendations. In my architecture, you can see that your process data is collected in its standard way into a PLC, HMI, or data historian. Afterwards, we're manually extracting that into CSV and uploading it into our cloud-based application. You can see that the user can interact with that application to get recommended set points. And again, those are manually entered back into the control system. Hence, we've got dashed lines in the collection of data and the return of data to your process. Now in level 2, we're automating data collection. So you can see that we've got solid lines from your current point of data collection to the application. And this is enabled by our edge device, which is designed to tie into most common industrial protocols. Finally, in level 3, you see all lines are solid. At this point, we achieve optimal closed loop control because set points are written back to the controller automatically. Just to recap what you need to get started before I switch over to the demos. In terms of data, we need things that you likely have, those process set points and the measured output you're trying to optimize. And in terms of connectivity, as you saw on this slide, it can be very simple with no changes to your current infrastructure. I'm now going to switch over to the demonstrations. Just getting it set up here. Great. Perfect. So in this first demonstration, we're at the lowest level of automation. So as I mentioned on that previous slide, there's a little bit of manual effort in terms of data collection from your process to build this model and to retrain it as we're going through optimization iterations, and to pass the recommendations back to the controllers. So the application itself is pretty straightforward to use, and its exact configuration will vary slightly based on the use case. However, here, I'm going to start by defining the objective. It's going to be to minimize a KPI, in this case, a final degree of fermentation. As I mentioned, the user can define constraints. So we'll limit the pH range to be less than or equal to some value 4. And then this is the search space for the control parameters of the process. They're predefined based on historical values that have been successful for batches. but the user can further narrow or widen these as needed. And that's it. So next we'll go ahead and click generate recommendation, and you'll see that a set point is going to be presented to the user. Now, this set point, so you see for each control parameter, we get a recommended value. This is going to be passed on to the operator to be manually entered into the process. The results will be collected and then returned to this application so that we can learn from every batch. Something important that I want to note, this set point doesn't have to be executed exactly. So let's say you don't have perfect control on your process. It's just your ability to achieve your set points is not ideal. This algorithm can still learn from that. So it will learn from any process variability as long as there's some fluctuations from your standard recipe. That's it for this first level of automation application. I'm now going to switch over to the second application. And after I've covered both of these, we'll go through the results that the clients who have implemented this have been able to achieve. Perfect. So now this second demonstration, it's at the highest level of automation. So we're streaming data directly from the process and we're writing set points back to those controllers. This screen that you're seeing here is the user configuration screen. On the left-hand side is where they make their inputs, and on the left-hand side is where they make their inputs. And on the right-hand side, this is displayed visually, and I'll get to that shortly. Now, as we saw before, I define my objective. In this case, it'll be to maximize the yield. I can build constraints, and then I've got control parameters. So here in this dropdown, I've got all the control parameters of the process. And here below, I've got actually a set point schedule, no longer just a single set point, but it's as I said, a schedule. So at different timestamps, we can change the set point of this process. One thing that I want to note, when this client that we deployed this for is actually in the process design phase. So all they have is the known ranges, acceptable ranges of their control parameters. They have their SME knowledge, so they have an idea of what a correct recipe will look like. And they have output specifications that their product must achieve. So this optimization application, it's actually going to do two things. First, it's going to find a suitable recipe to meet those output requirements. And second, it's going to further optimize that. Now on this right-hand side, what you see is that set point schedule for this given control parameter, the sugar feed rate. So you see an orange line, that initial value specified by the user. And then that light orange band is the search space that's available for the optimization application. So if I switch over to another one, you can see how it changes respectively. One more thing to note on this page, each of these set point changes is a decision variable in our optimization problem. So this will, you can see that there's a lot of decision variables in this particular application. The last thing the user has to do is define the number of runs that they have available to explore over which to explore this optimization. And here I'm just going to set it to 10. Now I do have an optimization completed, so I'll switch tabs shortly, but essentially this front end, I've linked it to a penicillin simulation, the same one that Xiao discussed in his slides. So in this case, we're passing set points to that simulation and returning quality and process values to learn for the next iteration, but that would be the same would apply in a real process, and it has applied for a client, where instead of a simulation, we're passing to a PLC controller, we get those results to update prior to the next run. So just in the interest of time, I'm switching over to this completed run with 10 runs. What you see on the left is a detailed set point schedule for this particular control parameter for the latest run. On the right, you're seeing the profile for all the different control parameters is available. And here you've got profiles for some key outputs. So you see the pH, the actual penicillin concentration, and the temperature. The colored line is the respective run. And in each graph, I've also got the best run so that you can see for comparison. Now, if we jump back up to this top graph, this is the objective value for each batch. So in this case, I wanted to optimize my yield. Now you see that early on, we do see some drop. And as I mentioned, we're optimizing over a significant number of decision variables. In fact, there's over 80 in this problem. So each timestamp of those set point schedules is a decision variable. It's natural to see some decay here as the algorithm is exploring the design space. I'm actually going to switch over to this other tab where I've run 50 batches. And you see that actually by around batch 17, possibly even as early as 10, we start to see some stability. And we do see some lower yield batches, but that's because the optimization, the algorithm continues to explore the design space. It learns that these are areas it will aim to avoid in the future. Two more comments with regards to this demo. These batches, so they are 200-hour batches, is what the simulation takes. So the simulation does not take that long, but the process is a 200-hour process. Now this, you wouldn't have to run this over 10 or 50 batches in sequence. If you have multiple lines at your facility, you could actually get multiple set point schedules or multiple individual set point recommendations at once to run multiple optimal set point recommendations in parallel to reduce the amount of time that it would take to find optimal conditions. And the last thing, because we deploy this online, it's not just for finding a single static recipe, but we can incorporate those ambient conditions, as I mentioned earlier, and we can continue to optimize in an ongoing manner so that you're always achieving the best outcomes. With that, I'm just going to switch back to my slide deck to present the results that our clients have achieved with these two applications. So now that first application, it was, so I demonstrated with no data connections for reading and write back. It was deployed for a global food and beverage manufacturer. The key challenges being faced at multiple client sites were achieving high process performance and consistency between their batches. Moreover, operator knowledge across sites varied. So when process upsets occurred, there was no standard method to respond. Now, by carrying out a 4-month pilot where recommendations were implemented on 20% of batches, the primary objectives were achieved. The performance of the process improved by 20% and variability reduced by 49%. Our easy-to-use application, which continuously learns from the latest process results, it actually acts as a tool for knowledge transfer between operators and a starting point to find the optimal conditions when process changes occur. Now, additional benefits resulting from improving the process was a 16% reduction in cycle time, which increased the manufacturing capacity at our facility because the step that was tackled was the bottleneck. Combining the overall improvement in yield and this improvement in this increase in potential capacity, we're looking at a potential annual productivity increase of 38%. And I'll reiterate, this was all done with offline set point recommendations, no changes to the existing OT infrastructure. We're manually extracting data and manually writing those set points back to the controllers. If we look at that second application, now, as I mentioned, the client using the second optimization application is in the process design phase, specifically for manufacturing pharmaceutical APIs. Now, this client is working with a novel reactor technology for which they need to design, as I mentioned, and then optimize the recipes for a range of pharmaceutical ingredients. Moreover, they're in a highly regulated industry, and they're interested in understanding the process design space for future real-time release objectives. So that second application that I demonstrated is achieving both of these objectives. It iterates to find a recipe that satisfies all output specifications and then optimizes it based on the objective selected by the user. Also, through the exploration, it inherently maps that design space for future real-time release objectives. The estimated impact to the business is actually a 434% reduction in time and effort associated with achieving these objectives using traditional manual methods. With that, I'd like to conclude my presentation for today. So thank you everyone for your time, and I hope that I was able to achieve my two objectives of conveying to you that the barrier to entry for process optimization is not high from data and automation standpoints, and there's significant business value in pursuing even the most basic optimization implementations. With that, I'll turn it over to you, Charlie.
Thank you, Manuel. And I'm just going to switch here. We have another poll question I want to present to people. And the poll is, how would you apply, or how are you applying ML-driven optimization to your manufacturing processes? And select all that apply. And there are different things that you could do. And so we're just curious what people are doing or want to do. All right. So the top ones that are coming through are reduce batch variability and capture process expert knowledge. Interesting. And there's a reason why we asked these questions. And what I want to show you here is, so for those of you who are looking to apply ML-driven solutions in the coming year, we've decided to simplify the path to process optimization. So what we're doing, we're currently offering free 1-hour consultations where we can discuss your problems, offer some initial ideas on solutions, and assess if our solution is a good fit for you. Next, we work with you on a short-term pilot project to prove value based on jointly established pilot success criteria. And the cost of the project is tied to your success criteria. So should we fail to meet or exceed your criteria, the pilot project is free at no cost to you. And then when you're ready to deploy, we are so sure of the improvement we can bring to your process. We guarantee a 10x return on your investment based on jointly agreed value criteria. And if we don't meet those criteria, the solution is yours at no cost. And so if you're interested in this, go to www.quartic.ai/optimization to put yourself on a path to process optimization, or you can contact us at sales@quartic.ai. And so go there to see more about the offer and let us know if you're interested. That concludes our webinar for today. Let's open it up to questions. I see some already coming in, and place it in the chat window or in the Q&A part. So I will now start reading them. So here's a question. I think this is more for Xiao. How can I get started with ML AI if I have very little data from my process, few batches and results? Is there anything I can start with, or should I focus on data collecting first?
So basically, if you only have a few batches, you can still start with the optimization that we have. It's just that you have to make sure the data quality is sort of good in a way. So that we can help you assess, see if so basically, if you have small data, but the data quality is sort of good, then you are good. If it's like you have small data, but then you don't know if the data quality is good or not, then we can help you assess that. But if you know for sure your data is like all over the place, and it's just like you have like 3 data points, then maybe you should try to fix the process first.
Good. Here I have another one. What kind of expertise and background is required to use these applications? So that I'd like to do 2 there. So Manuel, if you could talk a little bit about what you showed, but also Russ, what you see is required for folks to be able to use AI in ML in optimization. So Manuel.
Absolutely. So with regards to the applications that I demonstrated, they're really intended, and the application that the platform that we have behind these applications is intended for the process experts or the subject matter experts. So there is no requirement to understand the underlying algorithms to be able to program things like that. As long as we work with these process experts in building, converting the use case into to define it as an optimization problem. And then they can be training is provided for these users, and we find that they learn quickly, and they're able to execute these optimizations on their own going forward after we've done that configuration and training.
And Russ, I'm more curious in terms of your perspective of as AI and ML gets adopted for optimization. What do you see as the need in terms of the expertise and background that and the way of thinking that folks might need?
I think Manuel was spot on. The user of the software doesn't really need to understand all the details of how the software is working, but needs a qualitative understanding of what optimization is seeking to do. And so I think a qualitative understanding is adequate, but what Manuel also said was that you need to be the process expert, because you do have to understand your process, what you can change, what your limits are, what the context of your process is so that you can define what the objective would be. So really, it's more process domain expertise that's required, and just a qualitative understanding that optimization is seeking the best. So I would say exactly the same thing Manuel did, just different words maybe.
A lot of great questions here. Here's one that really interesting. So what kind of support is available for the validation needed if this will be used for GMP use cases? So I guess that would be you, Manuel, right? To be able to answer
Absolutely. I can take that one on. So our full solution, and we've been working hard in the last few months to build a full validation packages for these solutions, and we would support. So these validations are for GMP purposes. We would support the client in executing the protocols in these validation packages. And with regards to the actual underlying models and things like that, we've seen from regulated industries like FDA high-level guidelines, but not necessarily check marks that have to be achieved. So in that same idea, we would work with the client to identify the users that will. It's more along the lines of a workflow to develop and deploy these models based on the user experience. So who has the privileges to do that, and defining those workflows with a GMP mindset. So we would work with the client to execute both that validation package for the underlying the applications, all the software itself, as well as for the respective models that are being deployed and used.
Thank you. And this one's probably more for Xiao. It's more of like how to get started. So the question here is, do we need to have a simulation of the process, or are the set points and measure results enough to get started?
Right. So the set points and the measured objective are enough to get started. So as Manuel showed for the first application, that was exactly what we did, just collecting the set points only, as well as the measured outcome. And if you do have a simulation, definitely that will help. That will make your improvement more significant in a much shorter run.
Thank you. And here's another question. Can this optimizer be used in product development in addition to manufacturing? For example, with the design of experiments, can the optimizer suggest multiple experiment settings that could be run in parallel?
Right. So yes. So for design experiment, I would say it's easier than running your optimizer on production in theory, because the design experiments, that means usually the cost is lower if something goes wrong, right? So that means actually you can be a little bit more aggressive in the design experiments. That means that you can potentially have better improvement for getting the final result from that design, and you can definitely suggest multiple runs for it's kind of like doing experiments on similar assets, right? You can run multiple runs. Definitely, you can do that.
Right, thank you. And then I have one for Russ. So you had previously mentioned that the integration of this optimization idea. We were talking about the business objectives, but you were also talking about the integration with other operational systems. Can you talk a little bit more about that?
Yeah, right now, the major one that I see is that we have steady state models, and I'm mostly involved in the continuous processing. We have steady state models that we use to define set points. These set points are then downloaded to the controllers that keep the process under control. And the models that we have for steady state optimization are different from the models that we use, the dynamic models in control. And so there's inconsistency between the models and the results that you get. The controllers are tuned not for an economic optimum path, but for a comfortable balance between speed of removing disturbances or speed of getting to a set point. a comfortable balance for the operators, the operating staff, who have to listen to valves change on there. And so the path is not an economic best path back to the set point on there. So I think we have major opportunities with this in combining the two optimization steps and using the same model for control as we do for steady state optimization, and using the same model in one step, moving us along the optimal path toward the optimum, not just the optimum. And part of what Manuel was showing for batch processes, a sequence of set points that were optimizing the endpoint of the batch. So I think there's a good way to achieve this with batch processes.
Thank you. And with that in mind, the business objectives, if my optimization objective changes, right? So in this case, I was doing improving yield, but what if I want to save energy, right? For some reason, for a cost concern. Is there a way to be flexible to change towards this new objective? So how does that work in practice?
I can take that question. So yeah, so definitely that happens, right? And honestly, that's the one of the advantages of using AI for this kind of problems, where the underlying model doesn't have to be changed. It's really like, you can transfer the knowledge from the one task, which is improving yield, to the second task, which is saving energy, for example. And you don't have to start from scratch for the second task. You can transfer the knowledge from the previous model to this new model, and then you can get a quick jump start on that.
So you don't start from scratch, right? You
No.
already have something to get. Okay.
Right.
And this one is one also that's an interesting one. So my plant is a production line with many of the same assets performing the same function. So the question is how do I apply our optimization to these assets one at a time, or are all assets of the same type? So I think this has to do a little bit with how we attach what we're doing to the different assets. So who could answer that?
I mean, I can go first. So from algorithm or AI point of view, it's really a good problem to have. So if you have multiple assets, they are sort of same configuration and everything. It's great for AI to actually learn from all of them at once. So yeah, so definitely all assets are the same type. That being said, usually we also had clients who actually had similar problems, but when you dig deeper, you actually find that some assets might be doesn't have a lot of variability compared to other assets, although the configuration is same. So that way you have to kind of carefully handle them in sort of different ways. But overall, you should still tackle them simultaneously. That makes your AI model much quicker.
Would the device ID also be part of that, just in case there's variability across the devices? Is there a way to capture that or discover that?
Yeah, so it depends, but really I think a general answer to that is it doesn't have to be. So really the knowledge is about the process itself. So if it's like other things that are sort of not that unique, for example, device ID or whatnot, where it's not sort of important to the AI algorithm, then you don't need those things really.
All right. I don't have any further questions. And so with that, I would like to say thank you to everyone for attending, and we hope that this session was informative. And if you'd like to discuss specifics about applying ML to process optimization, please reach out to us. We will follow up in the coming days with a link to the webinar recording, and please feel free to share with any colleagues who might be interested. This will be available on demand. And please follow up on our LinkedIn homepage so you can get notified of our upcoming webinars. And once again, I'd like to thank you for joining us, and I'd like to thank Russ, Xiao, and Manuel for a great webinar. Everyone have a great day.